This is 10.3 parametric equations in calculus. Now that we learned how to um, how to draw the graph with parametric equations, um, let's look at the calculus aspect, which means how do we find the slope, the tangent line to the curve, how to find the area, how to find the surface area or the arc length, or those type of topics that involve the parametric equations. Now, because parametric equations involve two equations in terms of a third parameter, t. Of course, one way to do it, you have to find the derivative. For example, finding slope, the tangent line, you can use the technique of eliminate the parameter t like we did in 10.2. But notice that many times when you have the parametric equations, you won't be able to do that. It's just too difficult to eliminate parameter t to do that. So the question is, when we are given a parametric equation, say, right, x equal to t squared minus 3t, and then you have y equal 700t minus sine t, for example, right? If you're going to find the derivative, okay, so you can find the curve here for the slope, the tangent line, then you do need the slope. But the slope is the derivative of y with respect to x, right? That's the change of y with respect to the change of x. Now, if we had one equation, x and y, then it can do it explicitly. Since we don't, then we need to develop another formula to find the derivative without putting it back in our Cartesian equation. It turns out it's pretty simple. If you want to find the derivative of y with respect to x, all you need to do is you take the derivative of y, so this function y, with respect to t, divided by the derivative of x with respect to t. So what it means is, you just look at this y function, you take the derivative of that with the t as a variable. For example, here at 7t to the half, right? So you take a derivative. Half times 7 is 7 half time, then t to the negative 1 half, minus the derivative side of t, what the derivative side is cosine of t, divided by what's the derivative of x. Well, this is the 2t squared, right? So that's 4t minus 3. That's it. So all you do is take the derivative of y divided by the derivative of x, all with respect to t. So that's pretty quick. However, the drawback is your derivative formula is now written in terms of t rather than x. Okay, so that'll be in terms of t. Now let's go to the formality. Here's the quick definitions. Parametric form of derivative. If a smooth curve is given by the equations x equal f of t and y equal g of t, right? So you have the formula for x, formula for y, then the slope of the tangent line to the curve at the point x, y is dy dx equal dy dt over dx dt. Okay, so again, this will be dy dt, just the derivative of y, and that's the derivative of x. We could also think of that as fractions. If you have fractions divided by fractions, really the dt cancel out, so you see that's the same as dy dx. Okay, all right, let's take a quick look at the example down here. Find the slope of the tangent line to the curve given by x equal 1 plus 4 cosine y equal negative 3 plus 2 sine t. Again, I can write that in like a system equations. X equal 1 plus 4 cosine of t, and then the y function is negative 3 plus 2 sine of t. And we want to find the slope of the tangent line at this point, 5, negative 3. Right, so again, to find the slope, you need the derivative, right? So I'm going to start with the derivative of y with respect to x. And again, it's just taking the derivative of y here, divided by the derivative of x. So negative 3 here is 0, and derivative of 2 sine is 2 cosine of t. The denominator is the derivative of x, right? So that's 0. Derivative for cosine is negative 4 sine of t. So when you simplify, it's really negative 1/2 cosine t over sine of t. If you like, you can combine it into a new function cotangent of t, right? You don't have to do that, but put it in cotangent. Now, once you have this slope, the derivative, you can find the slope. Now, in Cartesian form, remember when you take a derivative of y with respect to x, that has to be in terms of x. So let's say you got that, right? So he's say that derivative. Again, just make it up random. When you take a derivative, well, it's going to be in terms of x. You need to find the slope of the tangent line, say, at the point 5, negative 3. This is x, this is y. All you do is you plug 5 into here, right? You plug into here, and then you can do the math, and I can get the slope. But our slope or the derivative is in terms of t. So you see there's a bit of trouble. We given x, we given y, but I cannot plug in because the slope, this derivative function has no x involved. Okay. However, I don't think it's too hard to do, but think about this. X, y, and t are related. Okay, so they are related. Remember, related by this table, where when you plot points, remember when you plot points t, x, y, right? And then every time you have the point, say with t is 0, you plug in t goes there, and then you got the point, and then your t is pi half, right? And then you plug in, you calculate, you got the x, you got the y. Now this time it's a bit, we go a bit backwards here because we know x is 5, y is negative 3. So I know the x is 5, y is negative 3. I want to figure out the corresponding t. Because at 5, negative 3, you basically want to find the t values for which x is 5, negative 3. And that'll be the t values you plug in here to calculate the slope at that point. Right, so how do we do that? Well, if x is 5, y is negative 3, you see that we end up solving the system equation, right? If x is 5 and y is negative 3, then I need to solve for t. You solve for t. Well, that will be what? 5 minus 1, I got 4. 4 equal 4 cosine of t. And I got 0 equal to sine of t. Well, the cosine, 4 cosine equal 4, cosine of t has to be 1, isn't it? And sine of t got to be 0. Okay, so we got that. Right, so what gives you cosine 1 and sine 0? So what values of t? I think clearly you can see that t has to be what? 0, right? So when t is 0, cosine 0 is 1, sine 0 is 0. So therefore, that is 0. So that is where I'm plugging in. Okay. So at 5, -3, at the point 5, -3, the t values is 0, and therefore the slope of the tangent there will be -1/2 cotangents of 0. Well, you might not see it well, but if you recall the cotangent cosine of a sine, if you plug 0 in, you actually have sine of 0 at the bottom. So that is 1 over 0 here. And 1 over 0 is undefined. So that is undefined. So what do we know? Well, slope is undefined. So there's no slope there. Okay. So the answer is undefined slope, no slope at the point 5, -3. Well, in fact, we actually have the vertical asymptotes there. That's why it's no slope, because the vertical line has no slope, right? Now, let's talk about the second derivative. What if we have to find the second derivative of a parametric equation? Now, with the second derivative, things got a bit more complicated, so it's not as uh, simple as we might thought. Okay, so here's the reason. To find the second derivative of a curve, we find the derivative of the first derivative. Okay, so by definition, right? So this is second derivative notation. Second derivative y with respect to x. That is the derivative of y prime, right? The first derivative with respect to x. Now, because the y prime is the functions of t, remember, functions of t. So that is the derivative here. You see that y prime. So this is your y prime here. That one, right? So you do second derivative. So this is in terms of t. Now, remember our formula for the derivative. If you take a derivative of that respect to x, that'll be the derivative of y prime with respect to t divided by derivative x with respect to t. So again, we have two parts. Derivative of the first derivative with respect to t divided by derivative x with respect to t. Okay, so if you do that, we should end up with 3 steps. The first derivative, right? We find the first derivative as always, right? The first one. And then you have to calculate the derivative of the dy dx, the one we just found, with respect to t. And then we divide it by derivative x with respect to t. Right, so let me go over quickly here so you can see what I mean. Let's use this example up here. So the derivative we found, okay, the derivative we found here is what, -1/2 cotangent of t, right? If we have to find the second derivative, so here's a formula. It is dy prime over dx dt. So that is, I need to find the derivative of this. Let's do that. -1/2. Well, what's the derivative cotangent? That is negative cosecant squared. So that's cosecant squared t. Negative cosecant squared. With the negative, so make it positive. Now, it's oftentimes or the common mistake that this is the answer. Now, this is not the answer. This is just the derivative of the y with respect to t, which is the numerators only. So the second derivative is this, half cosecant squared t divided by dx dt, which is again back to the derivative of x is here. Its derivative that is the -4 sine t. That is the second derivative. Okay, so make sure you take a derivative of y, derivative y prime over derivative of x. Originally, the first derivative y over derivative x. Here's a derivative y prime over derivative x. Okay. Let's look at the example here. Right, so I have the parametric equations is x equal t minus t squared and y equal t minus t cubed. Okay, then to find the second derivative, again we asked to find the second derivative. Then we have to find the first derivative, right? So find dy dx. So that's the first derivative. So the y prime, so dy dx, again, it's just the derivative of y divided by the derivative of x. Now, you probably don't need to write the step down, but you can just take a derivative of y, which is 1 minus 3t squared, divided by the derivative of x, 1 minus 2t. That's it. Okay. So again, the first derivative is 1 minus 3t squared over 1 minus 2t. Okay. Derivative y with respect to t over derivative x with respect to t. So that's the first derivative. Now for the second derivative, we will looking at the derivative of dy dx. Okay, that is, we're going to take a derivative of that one. Now in this particular case, it's a bit more complicated because the derivative of this, it is a quotient. So don't forget that when you're dealing with quotients, the derivative of quotients, u times v. So that is u prime v plus v prime u. Okay, the first time, the second plus, sorry. I'm talking about the quotient rule, not the product rule, right? So it'll be u over v. So it'll be u prime v minus v prime u over v squared. Don't forget the v squared bottom. So taking derivative of that, you're actually doing derivative top. What's the derivative top? It's -6t, right? 0 minus 6t. Time v is this, is 1 minus 2t, minus derivative the bottom is -2 times 1 minus 3t squared all over the bottom 1 minus 2t quantity squared. Right, so when you multiply out, it'll be -6t plus 12t squared, right? 12t squared. This is positive 2, and then distributed in become -6t squared. Again, everything over 1 minus 2t quantity squared. And notice that we have two like terms here. 12t squared minus 6t squared. I think we have 6t squared. Then we have the 2, we have minus 6t plus, all right, so it's over 1 minus 2t squared. See, that's what we got over here. After applying the quotient rule, now that's what we got. And don't forget that the second derivative now is dy prime over dx dt. So that is what we just got divided by derivative x here, which is 1 minus 2t. And we simplify, it'll be 2 minus 6t plus 6t squared over 1 minus 2t cubed. Okay. Now, so that's how we find the second derivative. But when we got the second derivative, how are we going to use that information? You recall in Cal 1s, what does it tell us when it comes to the second derivative? You forgot, please, quick review. If the second derivative is positive, the graph is concave up. So this is how I remember positive, right? The graph will concave up, curve this way. And if the second derivative is negative, the graph will be concave down. Okay, concave down. So I have like happy and a sad face, basically tell you that when a graph concave up, when the second derivative positive, and concave down when the second graph, when the second derivative is negative. Right? So let's use that information to looking at this example here. Right, so again, I have the same graph, x equal t minus t squared and y equal t minus t cubed. If you graph this on the calculators, that's what it's going to look like. Okay. The question is this parametric curve concave up or down at this origin here? And again, the question is, at the origins, is the graph concave up or concave down? Now you see that it's a bit complicated here at the origin because the graph crosses itself. If you look at this piece, it looks like the graph is concave up, it curves like the U-shape up, right? But then the other way, if it's on the way down, the graph seems to curve the other way at the origin, so it's actually concave down. So even at the same point, but it depends on which part of the graph, then the concavity will be different. Okay, so again, how do we know concave up, concave down? It's boiled down to the second derivative. Well, we have the second derivative already. Okay, so I'm gonna do this. Okay, going with what the second derivative, right? So the second derivative we just calculate is 2 minus 6t plus 6t squared over 1 minus 2t cubed. Now, we want to know at the origin, right? So again, at the origin, that's when the x is 0 and the y is 0. Now, our second derivative involves t. So I have no idea what to plug in because that in terms of x and in terms of t, but our given information is in terms of here I know x is 0, y is 0. So you see that again, we kind of go backward here. If you know x is 0 and y is 0, can you figure out what t is? So that would again involve solving the system equations when x is 0 and y is 0. So you have t minus t squared 0 and t minus tq is 0. Well, factor out the t, I got 1 minus t here. Take out the t's, I got 1 minus t squared. Okay, and I can factor further, that's t, it's 1 minus t times 1 plus t, it's difference squared. The first equations, I get t equals 0 and 1. The second equation, we have t equals 0 plus and minus 1. You see that 1 is negative 1. So we have 3 solutions for the second equation and 2 solutions from the first. So which one do we pick? Remember, we want both x and y to be 0. That means I need to choose the t that satisfies both equations. That means you're going to choose the one that they are common solutions. So 0 and 1. So you see that we have 2 cases when t equals 0, versus t equals 1. In fact, when t equals 0 is when the graph is on the way up, and then t equals 1, the graph's on the way down. So that's why you see that we can have 2 answers here. When t equals 0, plug in to the second derivative. I got 0, 0 here, so it looks like we have 2 over 1 to the third power 1, right? So that's positive. So the graph is concave up. And if t equals, that is supposed to 1, be 1. So if t equals 1, then I plug into the second derivative. 1, so be 2 minus 6 and plus 6 again. But the bottoms, I have 1 minus 2q. So that's 2 over negative 1 to the third is negative 1. You see that is less than 0. So the graph is concave down. You see, concave up here, then concave down. All right, I'll stop here for the first part.